We'll be talking today about batch inference and about how Daft optimizes that using prefix caching and continuous batching. To get started, let me give a quick intro about myself. Again, I'm Kevin. I work on Daft. I lead work currently on our batch inference, performance, and scalability. More generally, I work on APIs within Daft to run AI code at scale. So not only is that inference, but also like doing things like running your Python code, your like custom models within PyTorch, stuff like that within Daft. I also worked significantly on much of Daft's query optimization and Python APIs. So yeah, previously I worked in the quantitative finance world, where I did a lot of work in the distributed data processing and inference side of things. And I was also at UC Berkeley, where I focused my studies largely on AI and data systems, including some research into vLLM, which is a serving engine that we'll actually be talking about today. So quick summary of what we'll go through today. We're introducing a new inference backend within Daft that essentially cuts batch inference time in half. The backend leverages several techniques that we'll discuss, including dynamic prefix bucketing, as well as streaming-based continuous batching. And for a representative inference workload, we chose a 128 GPU cluster, an 8 billion parameter model on 200,000 prompts with around 128 million tokens in total. We saw that within our benchmarks, combined, these techniques helped us reduce batch inference times by 50.7%. And if you want to try it out, all of the stuff that I'm going to talk about today is already released within Daft. And so here's an example script of how you can run it. The functionality is provided via the prompt function that you can import from Daft.functions. And then you can give it a input column, as well as the provider, which is the vLLM prefix caching provider, and a model to run on that column. So a quick introduction about what Daft is. Daft is a data engine that gives you the power to, 1, run models over your data, 2, work with your multimodal data, and 3, scale your AI data workloads up to thousands of nodes, up to petabytes of data with Ray. It provides a Python native data frame API, along with native image, tensor embedding, file, and other multimodal data types. We also have powerful built-in AI functions. Prompt is one of them. Another one, for example, is embed text, which I'm showing here. This quick example is some Python code where you're constructing your own Python, custom Python logic to extract content from documents, and then reading a Hugging Face data set where you're first turning the URLs into Daft file data types, then using your custom Python code, aka like a Python user-defined function, to extract a text from that document, and then run with our native embed text function, embedding models over that, over those extracted texts, and then writing it out to a vector DB, in this case, TurboPuffer. Some of the common use cases of Daft are embedding generation and ingest, structured data extraction, as well as content deduplication. So for embedding, I showed you a quick example earlier. Basically, we support reading data from wherever you store your data, Parquet, S3, Iceberg, Delta Lake. We can easily use our built-in embed text and embed image functions to generate embeddings from them. And then we also support native writing to your vector database. For structured data extraction, what users do is they write Python code using the Python libraries to extract, say, text from documents, do like feature engineering with like images and video. Then with our file and download APIs, work very natively with URLs, with files all in distributed scale. And you can also use our prompt function to generate structured outputs natively within Daft. Finally, for content deduplication, this is a use case where you may have like data that you want to use for training, and you want to, say, deduplicate that data and clean it up before you pass it into your training pipelines. And so we support things like exact, min-hash, and semantic deduplication. And with our distributed engine running on top of Ray, we allow you to scale that up to terabytes of data that you're able to dedupe. Cool. So let's talk about batch inference. There's generally two different classes of inference on LLMs. The first one that you're probably more familiar with is online inference. This is where you have real-time requests, such as when you're doing ChatGPT conversations, IDE code suggestions, or like the real-time agentic workflows. And what matters in these cases is often, one, time to first token for interactivity, as well as the tokens per second on an individual request, the throughput within a single request. On the other hand, for batch inference, we're doing things like preprocessing an entire data set offline for computing embeddings for vector DBs, labeling data, or generating synthetic data for training, right? And what matters in this case are, one, tokens per dollar, and two, the aggregate throughput or aggregate tokens per second instead. There's also a few unique challenges and opportunities that batch inference provides that we'd like to exploit within Daft. The first one I've discussed already is performance. The second one is the size of the data. In online inference workloads, you're typically not going to run into like memory limits with the number of requests that you have. You're typically going to run into limits in terms of the inference throughput instead first. But with batch inference, your entire data set may not actually fit into GPU or CPU memory, so how do you handle that? Another axis is cost and GPU utilization. For online inference, your cost depends on either the total number of tokens that you're running through inference, if you're using an inference provider, or some fixed amount per hour if you're like self-hosting your own models. On batch inference side, the cost is largely tied to the GPU hours that it takes to actually run inference over your data. So effectively utilizing your GPUs while you're doing the batch inference workload is highly essential for that. And finally, the final axis that we'll discuss today is data distribution. For online inference, since your prompts arrive real time, you can't really know the future data distribution, right? You don't know like if a user sends a message, to ChatGPT, what's the next message that they're going to send. Whereas in batch inference, you have a data set of prompts, and so you know all of them in advance, and we can allow for some further optimizations that rely on the distribution of your data. Cool. So the workload that we're going to discuss today, relatively simple, reading a data set of prompts, generating outputs with LLMs, and then writing out the outputs. And let's see how well we can do that. Specifically, we're going to generate 200,000 prompts with a 8 billion parameter model, and we're going to use a Ray cluster with 128 GPUs, a pretty large, substantial Ray cluster. Okay, so the first technique that I'd like to introduce is naive batching. And with that, it's fairly straightforward. You have your data set, you split it into some batches that are small enough to fit into memory. Then you send it to these N replicas of your LLM serving engine. In this case, we'll be using vLLM. And essentially, you just after you split your data up, you just pass it through sequentially to each of your LLMs, right? This is trivially scalable. You just scale up the number of LLM nodes in your cluster, and you scale and you divide your data further as needed so that they're well balanced across your cluster, right? If you do this, you'll run into a few issues or into a few things that you encounter. The first one is that you'll see that GPU actually sits idle between the end of computation for one batch and the start of the next one. This is because pre-inference and post-inference steps are required between these batches, including things like tokenization, data transfers, and batching. And while those are being done, your GPU sits idle. Additionally, within a batch, some requests will complete before others, and so you'll see a lagging tail of longer sequences that are being run, whereas the previous ones are finished. And so what you'll see is something like this, where the top side, above this line is GPU compute, and below is CPU, and you'll see a bunch of gaps some of them because of the pre and post inference steps, and some of them because your sequences take different amounts of time to complete. So how do we solve that? Well, introducing continuous batching. vLLM, the serving engine, supports a technique called continuous batching, where inference is batched instead of on a per sequence or per request level, it's batched on a per token level. So what this essentially allows us to do is start inference on prompts in a subsequent batch while the ones in a previous batch complete. And there's great pipelining within that. Here's a diagram that I pulled from an AnyScale blog explaining continuous batching. Highly recommend reading this if you want to learn more about this. But essentially what's happening here is you have these 4 sequences from a previous batch. They complete at different times, and you're able to start the other sequences from the next batch as soon as essentially one of the sequences from a previous batch completes. And so GPU utilization is very high. On the Daft side, we need to do a few things to actually leverage this, right? So what we did was we built a streaming sink, which is a class of operators within Daft that stream batches through them while accumulating some state. And what the state is, in this case, is a buffer of input batches that is fed to vLLM. And we maintain essentially a large enough buffer such that whenever vLLM is ready for a next sequence to add to its continuous batch, it has something ready. And so GPU utilization is done or is high throughout the entire data set. And once the LLM engine completes a certain sequence, it pushes it into an output buffer that it accumulates and then is streamed out to later processing steps. With this, we get around 11% speed up over our naive batching workload. And so here's a diagram of how this would work. We have our batch queue that we had before of the data split into these small batches to send to each individual worker. But instead of passing it directly into vLLM, we have an input buffer that we fill with these batches that the async LLM plucks from when it is ready to receive another one. And then it puts the completed batches or the completed sequences into an output buffer that is then streamed to the next part of the query. So how can we improve further from that? Well, let's talk about prefix caching. So model prompts often contain repetitive content, things like system prompts, things like common instructions. If that is true, then we can leverage what's called prompt caching or prefix caching to avoid recomputation for a lot of the sort of computation that is required for those common prefixes. And so here's an example where you have 2 requests where much of the requests are the same except for just a little bit at the end. And what you can do here is that on the first request, you do need to compute the prefill step for the entire request. But on the second one, you can actually just leverage the cached prefill instead of recomputing it. So with vLLM's automatic prefix caching, the engine will attempt to cache the computed values of a sequence in GPU memory automatically. But again, there's some work that needs to be done on the Daft side to actually leverage this. In particular, there's 2 challenges that we face when we're trying to do this at a distributed scale for batch inference. The first one is cache evictions. So GPU VRAM is pretty limited, right? If you have 2 similar sequences that you're able to leverage a prefix cache for, but they are far apart in your data set such that they're not being sent to the serving engine at a close enough interval, your prefix cache may be evicted before you're able to process the next request. The second one is cache locality. In a distributed cluster, you have prompts that are sent to a variety of different machines, right? However, the prefix cache is local to a single machine or a single GPU. And so if the requests that share similar prefixes are on different machines, we're not able to leverage that cache either. So what's the straightforward solution to this? Well, we can just globally sort the data prior to inference, right? That way, all of the prompts with the same prefixes are grouped together, and largely that will be on the same machine. If we do this, we see essentially a 35% speed up over our previous continuous batching method. And our prefix cache hit rate, if you monitor that, you'll see that it goes from around 26% up to 54%. So the majority of your your key and values are actually retrieved from the prefix with this technique. And so here's a quick diagram again of how this would work. You essentially distribute your data across your machines. You do this distributed sort, an n-by-n sort of your data from all your machines to all your machines again. And then once you've sorted all that data, then send it to each of the individual LLMs for processing. Okay, but how can we do even better than this? Well, let's talk about dynamic prefix bucketing. So with a global sort, you see a few limitations. The first one is that sorting is a blocking operation, meaning that you have to wait for it to fully complete before you can do the next step in your pipeline, your inference step. And so while that sort happens, your GPUs actually just sit idle again. And so you're wasting like your GPU cost by doing this sort essentially. The other thing is that sorting your entire data set means that you have to materialize all of it into memory. And so if you have an extremely large data set, if you're working at a large scale, that might not be possible. So instead, we want a way to achieve high cache rates while still streaming your data through, not having to materialize all of it, and maintaining good like pipelining, while also having high GPU utilization and high prefix cache rates. And the technique that we've developed to accomplish this, we're calling dynamic prefix bucketing. Dynamic prefix bucketing consists of two components that I'll explain. One is local prefix bucketing, and the second one is prefix-aware routing. So let's talk about local prefix bucketing. What we're doing in this case is on each individual machine, so zooming into a single machine, we maintain a buffer of inputs that are bucketed by prefix. Whenever we want a next value to send to an LLM, we pop from the buffer the largest bucket. Additionally, we interleave these removals, these popping, with insertions into the bucket, such that if you have a smaller bucket, you'll eventually it won't get popped until it accumulates large enough. And so you'll have a large bucket or a large batch of common prefixes. How we compute these buckets locally is we sort the data. So imagine this is an input buffer here. We sort it into a sorted buffer, and with that, we're able to check essentially adjacent prefixes, and if they share a common prefix, then we put them into the same bucket. Okay, so we have these batches now via our local prefix bucketing that have common prefixes. Which LLM should we actually send it to? Well, that's where prefix-aware routing comes from. What we do here is the local executors, once they have a bucket ready, they query a global prefix-aware router to ask it where it should send the batch of prompts to. The router determines the best replica of the serving engine to send it to via two different considerations. The first one is cache locality. Basically, if one replica has seen a prefix before, you should ideally send it to them. But the other one is load balancing. If we have, say, a prefix that is common across a bunch of different prompts, we don't necessarily want to send them all to the same machine, and so we want to balance that across our cluster still. That way, our GPUs for all of the cluster are well utilized. So based on both those factors, the router responds to the local executor with the replica that a batch should be sent to, and then that local executor submits it to that executor to that serving engine to actually do the inference on. So what that looks like in this diagram is we have first our local prefix bucketing on individual machines, and then choosing the largest bucket on each machine, we then go through the prefix router to determine which LLM serving engine to actually give it to. And we combine this technique with our continuous batching. So by doing both local bucketing and global routing, we're able to improve cache hit rates across the entire cluster while also streaming the data through. And so GPUs are fully utilized almost instantly once the data is available, and full data materialization isn't necessary anymore, unlike sorting. The result is that we actually achieved 12.7% faster speeds than our previous global sorting technique. And in total, in aggregate, this is 50.7% faster than our baseline of naive batching. Our cache rates are also maintained compared to sorting. So sorting had around 54.5% cache hit rate for prefix cache, whereas here we have 54.0. So very similar rates, but with streaming execution instead. Cool. So let's look at the benchmark results. So to reiterate, we had a data set that we randomly generated with 200,000 prompts, 512 tokens each, so 102 million input tokens in total. We have 512 unique prefixes across the entire data set with 256 tokens in the prefix, so half the prompt is a common prefix. We're using the Qwen 3 8B model. For each input, we're generating 128 output tokens. For our hardware, we have a RAID cluster with 128 GPUs. These are NVIDIA L4s with 24 gigs of VRAM. And more specifically, we're using the G6.12x large EC2 instance types. And the methods that we're comparing are 1, our naive batching, 2, continuous batching, 3, the sorting and then continuous batching, 4, our dynamic prefix bucketing, and 5, RAID data, which is an additional baseline that we are comparing against. And so we see that with each iteration of the algorithm, we're able to achieve faster performance. And with naive and continuous batching, we see low cache hit rates. But with both sorting and dynamic prefix bucketing, we have very high cache hit rates. The results for RAID data are pretty comparable to the results for continuous batching, 869 versus 842 seconds in total. And that validates our approach because if you look into RAID data's implementation, they also do a form of continuous batching. And so we're able to determine that, like at least with our continuous batching approach, we're pretty much close to optimal performance. Right. We also did some scalability tests. So what this is we ran the same workload on a cluster of 32, 64, and what I showed before, 128 GPUs. What we saw is that we see near linear scaling around 97% from 32 to 64 GPUs, so this point to this point. And then decent scaling around like 90% efficiency from the 64 GPUs to 128 GPUs. Some possible limitations that we can further explore in the future that will help with the scaling are, 1, there is some set of overhead of loading the model weights somewhere between 30 and 60 seconds, and that's just fixed across the different sizes. And so as your actual inference time decreases, the model weight loading time starts to dominate. The second one is that there may be some limitations in terms of the scalability that Ray offers. And the third one is that there are some potential bottlenecks in the technique. And so these are things that we are going to explore in future work. We also did some tests on different prefix counts. So we have 64, 512, which I showed before, and 496 unique prefixes, as well as testing a data set where there are no common prefixes at all. And so running this workload, we'd see that the dynamic prefix bucketing algorithm seems to perform better as there are fewer unique prefixes, which makes sense because there's more prefix caching that you can leverage. but it's able to still maintain pretty good performance even as you increase the prefix count, right? Increasing from 64 to 4096, which is a 64x in terms of the number of unique prefixes, we're still able to achieve very similar performance within like 10%. Cool. So in conclusion, with our new technique, dynamic prefix caching, as well as continuous batching, we significantly improved the batch inference throughputs within Daft by up to 50.7%. And this feature is out in public beta right now in Daft since Daft 0.6.9. So try it out, and we welcome your feedback on this. You can do so by installing Daft with pip install Daft, and then running the code that I showed before using our prompt AI function. Just a quick shout out, if any of the work that I discussed here interests you, we are hiring. So we're hiring for these 3 roles. You can contact careers@eventualcomputing.com for more information. And join our Slack community to ask questions, to chat with other users as well. Yeah, and that's all. Any questions? Is there a microphone that we pass around? I'm just curious. If not, I will just choose you in the back, I guess. We have not, or not at large scale. We've tested some things at small scale. It seems to, what we've noticed is that like, as you increase the number of, like the percentage of the prompt that is the prefix, it scales like sublinearly, essentially. Like, if you sort of like double the amount of prefix in the prompt, I would say it more than doubles the performance of the prefix caching. Yeah, if you have like, if there's no like common prefixes, then this technique offers no like additional benefit over continuous batching. Yeah. Yes.
Does the prefix bucket size matter in terms of performance if you make it bigger versus smaller?
Yes, it does matter because like as you increase the bucket size, right, you're able to capture more of the prompts that have the same prefix. But also, if you increase it too large, what we found is that it actually impacts performance because if you have a large bucket, you're unable to load balance that across your machines like effectively. And so that's something that we offer as a tunable parameter in this function.
Can I set a TTL saying that if the bucket was not full after 1 minute, still send out the batch?
So eventually the buckets do get sent out at the end once like basically the entire data set goes through the local bucketing, right? And so like it will accumulate until it's like, as large as it can be. And then it will be sent out. And so I guess like there's no need to like specify it manually. Yeah. Other questions? Yes, you.
So like this presentation's LLMs, but I'm curious to use like Daft for vision encoding, like batch inference workloads. Would I see similar performance between Daft and Ray data if it's just continuous batching?
I would say so, yes. I mean, we showed with our benchmarks that with continuous batching, we're able to run very similar performance, right? If you're using custom models that are not LLMs, we have a very robust API that allows you to run your custom like Python functions within Daft with our daft.func decorator. And so you can do things like run an async batched function in which you get batches in an asynchronous manner, and you can do essentially what is continuous batching using that as well. Yes?
The system you built looks so flexible and elastic, so it's kind of hard to tell if it's a online serving system or offline serving system. So which is good, but for me, it kind of feels like the system does not have utilizing the advantage of offline batching, which is we know the data ahead of time. So do you think there is still room for improvements?
I think the intention behind this system is that it utilizes the fact that it is on offline batching, right? We talked earlier about the various differences between online and offline batching. Let me pull that up. And so we're able to utilize, say, the data distribution to do this prefix routing because we know the distribution of the data beforehand, whereas for online we can't, right? We are able to more effectively utilize GPUs because we're able to maintain a buffer of computation that needs to be done. Whereas for online, if you have just low number of requests for some certain amount of hours, you either need to auto scale your cluster or you'll just see low utilization, right? Whereas here we have a fixed size cluster and we're just essentially maximizing throughput through that cluster the whole time. And that's because we're doing offline inference. Yeah. Yes?
Have you done any work on the multimodal batch inferencing? Do you have any a case study to share?
Yeah, we actually very recently introduced the ability to add images to the prompt function. So I showed before, with this prompt, you give it a column of, currently for this one, it's a column of text, but you can also give it images along with text now, and you can generate actually structured outputs with the same API. And so that's something that we're actively developing right now. Yeah. Other questions? Yes?
Can there be different bucket size? Say I'm using different GPUs?
Yeah, good question. So that's something that I think will also be in future work, is essentially dealing with what we call heterogeneous clusters. Clusters with either CPU and GPU nodes or different types of GPUs. And that's something that we are thinking about and that we'll be working on in the future as well.
CPU offload also. Can I do some part of inference on CPU while my GPU is doing probably a very small batch?
There's a lot of nuance to that question. I would say there's a lot of steps before inference that you can do on CPU that you can actually distribute out to different machines. The sort of in tokenization and prefill steps. But if you're talking about doing some of the inference steps, running some layers of your model in CPU and then some in GPU, there's a lot of, I think it may be possible, but that's not something that we're currently exploring. There's a lot of questions around data movement that needs to happen to accomplish this. And so it may not necessarily be actually very performant to do something like that. Yeah. And I don't think that's something that many serving engines support either. I know that I'm not aware of vLLM supporting that either. So yeah. Cool. Any other questions? Cool. All right. Thanks for attending my talk. And again, join our Slack community.